myself some room. Move this whole train over here. Here we go. All right, so go ahead, Alan, you can start. Okay, so problem number 2, all right? We're not going to be told our equilibrium concentrations. We're actually going to be told about what's happening initially. We've got a mixture of 28 grams of nitrogen, 3 grams of hydrogen, and that is in a 1 liter flask. We're going to let it react, and then the only other piece of information we're told is that at equilibrium, we figured out, we were able to measure that there's 0.17 grams of ammonia present. From that information, we need to basically calculate Kc, which means we have to figure out the equilibrium concentrations of each of the chemicals. Okay? For this, I definitely want us to use an ice box, or if you call it a rice box. We're going to write our reaction, that's the R. And you want to draw your ice box right underneath it. Okay, so this is initially, this is how it's going to change throughout the reaction, and this is what it's going to be at equilibrium. And this is what we're after, because we just learned in the previous problem, if we have equilibrium concentrations, we can plug them into our Kc expression and get the constant, right? Okay, so what do we have initially? What do we know about our nitrogen?
28.
We have 28 grams of nitrogen. Can I put grams in my expression? No. I have to get it to molarity, don't I? So let's first get grams to moles. What's the molar mass of N2? Be careful.
About 28.
28 grams of N2 are 1 mole. So we actually have 1 mole of nitrogen, and I've made this kind of easy. Our flask is 1 liter. So what's 1 mole divided by 1 liter? 1 molar. So that was kind of easy. If this had been a 2 liter flask, we would have had 1 mole divided by 2 liters. It would have been 0.5 molar. However, whatever size flask you have, you use that as your volume. Okay, let's look at our hydrogen. We have 3 grams of hydrogen. What's the molar mass of H2? 2. 2 grams of hydrogen is 1 mole. And so don't we have 1.5 moles? And again, that's in a 1 liter flask, so we have 1.5 molar. And then how about NH3? What do we have? Initially. Is there any mention of NH3 initially? Right, only at equilibrium. So what do we have to assume about our initial concentration of NH3?
0.
It's 0. They have to tell you if you have some. This is very common to have 0 of something. Now if you have 0 of product, which way does this reaction have to go? It has to go forward. Reversible reactions can go both ways, but if you don't have any product, right, to react, then it has to go forward. Okay, so let's focus on the change, okay? And let's do it all in terms of x's to begin with. So, when this reacts, by what factor of x will n change? 1x. And will it go up or will it go down? It'll go down because the reactants are going to turn into products. So this is going to go down by 1x. What is this going to do? It's also a reactant. Go down by 3x. And what is this going to do?
Go up by 2.
Good. It's going to go up by 2x. That's awesome. So we're always going to fill in this x thing in the middle. Okay? Now, we have a clue about this right here, don't we? It says at equilibrium we have 0.17 grams of NH3 present. Well, 0.17 grams of NH3 is how many moles? What's the molar mass of NH3?
17.
It's 17, not a coincidence. So 0.17 divided by 17 is what?
0.01.
0.01 moles of NH3, and so our molarity, it's still a 1 liter flask, is 0.01 molar. So what is 2x equal to? 2x is equal to 0.01. If this went from 0 to 0.01, and that change is represented by 2x, then doesn't 2x equal 0.01? So what does 1x equal?
0.005.
0.005. Okay, so what I would like for you guys to do is I would like for you to use this x value that we just solved for to figure out these values right here.